welcome you all in today's NPTEL online certification course lecture on mechatronics. Today we are going to talk about myoelectrically controlled robotic arm. This example for the design of mechatronic system which I have taken is based on the textbook by Elseator and Histan. It is a very nice realistic example. So, those who want to refer in detail, they can refer that textbook. I will be giving the reference at the end of this lecture also. So, the goal of this project is basically to design a system that uses myoelectric voltages from a person's bicep as a control signal for a robotic arm. And you see these myoelectric voltages are very small in amount as well as they have lot of noise also in these signals. Okay. So, we are going to talk about all steps involved in design of this entire mechatronic system. Okay. So, the microcontroller based system design procedure actually consists of defining the problem and then drawing of a functional diagram, identifying what are our input output requirement, then selection of the appropriate microcontroller model and identification of necessary interfacing units, circuits, and deciding on what programming language we want to program the for the system, drawing of the schematic diagram and a program flow chart, and finally writing a code and building and testing the system. So, these are the steps which are involved in the microcontroller based system design procedure. So, we are going to discuss about each and every step. So, the definition of the problem, as I said, our aim is to get myoelectric voltages from a person's bicep as a control signal for a robotic arm. Okay. And from that, based on that signal, basically say we want to control a robotic arm. Okay. So, this project can be divided into three phases. One is say acquisition of data from the person's bicep, okay, and then classification of that data, and then ultimately the actuation of the robotic arm. Okay. So, these three steps we can divide this project into these three phases. So, what does these phases involves? Basically the data acquisition involves measuring and digitizing the myoelectric signal. Okay. So, first one need to measure and then digitize that myoelectric signal, and then classification, basically it involves estimating the muscle force based on the myoelectric signal. Okay. So, based on the myoelectric signal, we can estimate the muscle force corresponding to that signal, and then ultimately the actuation, that is moving a robotic arm to a position corresponding to that one, okay, corresponding to estimated forces. So, here as you can see here we have the data acquisition over here, and then this is your classification, okay, and here is the this is your actually the actuation. Okay. So, this is a symbolic representation of these steps basically. Okay. Then you see these myoelectric signal or surface electromyograms SEMG as we call it in short, are produced during muscle contraction when ion flow in and out of the muscle cell. Okay. And when a nerve sends the signal to initiate muscle contraction, an action potential of ions travels along the length of the muscle, and this ionic current can be transduced into electric current with the help of AGCL electrodes placed on the surface of the skin above the contracting muscle. Okay. And typically the greater the contraction level, the higher is the measured amplitude of SEMG signal. However, even if a contraction level is constant, the SEMG signal can be quite irregular, and the typical characteristic of these signals are amplitude is of the range of say 0 to 5 millivolt. You can see very small amplitude. Frequency range is 0 to 500 hertz, and the dominant frequency range is around 50 to 150 hertz. Okay. And as I said, these signals are very small in the millivolt range, say of 5 millivolt. Okay. And in fact, electrical noise on the surface of the skin can be of greater magnitude than the signal of interest itself. Okay. So, this is there. Next, what after specifying, next we look at the functional diagram. Okay. So, functional diagram basically we draw a block diagram depicting the flow of information between the system required components. Okay. And before digitizing the SEMG signal, it must be amplified to take full advantage of the input range of the analog to digital converter. And before amplification, we need to separate the noise, otherwise it will also be get amplified. So, here you can see that we get the signal over here, then the signal conditioning is carried out, and then we have the interfacing circuit basically which consists of your A to D conversion, serial interfacing, okay, and a microcontroller basically. So, the flow of signal is something like this. Your signal conditioning sends the signal, okay, to A to D converter, analog to digital converter, and these digital SEMG signals are then sent sent to your PC for classification purpose. Okay. And using certain program you can classify that, okay, and calculate the force, and this force estimation estimated is again passed through EMG signal to say PIC PIC microcontroller, and from this PIC microcontroller it can be sent to a robot, say ADAPT robot. Okay. We can also have a display over here just to display of give a visual display of the force which is being sent to be to the robot. So, we filter out the noise and amplify the signal prior to A to D conversion over here, and if you are not doing pre-filtering basically, okay, then we may have certain issue. Okay. And this data, this stage of data acquisition is as I said what we call it as the signal conditioning, and this digitized signal can be sent to a PC where muscle force is estimated based on the analysis of SEMG data, and as I said estimated force is sent via an interfacing circuit to the robotic arm. Now, the arm moves to a position that corresponds to the estimated force basically. Okay. So, for example, at the rest the robot arm will be at 0 degree, and at the maximum contraction level the robotic arm will be say kept at the maximum angle. Okay. And we can use as I said an ADEPT 1 MV robotic arm, which can serve as a good laboratory model for the prosthetic arm. Okay. So, its configuration is very similar to that of a prosthetic arm. Then next is about the identification of input out requirement and selection of the appropriate microcontroller model. Okay. So, here one can use a microcontroller dedicated to performing the analog to digital conversion and sending the digitized signal to a PC. Okay. Why we require analog to digital conversion? Because the myoelectric signal is actually the analog signal, whereas your system will be requiring the digital signal. So, we need to have the analog to digital conversion, okay, before it is being processed. Okay. So, ideally we can use the two microcontroller, one which can be used for analog to digital conversion, and another can be serve as interface between the PC and the robotic arm. Okay. So, here basically we can have the two microcontroller here. Okay. So, one for analog to digital conversion and another which interfaces between your system and the robotic arm. Okay. For the analog to digital microcontroller, the primary constraint is of course that it must have an analog input with sampling rate over 1000 hertz, because the sampling theorem, as we have seen, states that we must sample at least twice of the highest frequency component of the signal, okay, which is 500 hertz, as we have seen in the previous slides, after it is filtered. Okay. So, the sampling rate, if you want to if you want to sample the signal properly, the sampling rate frequency has to be 1000 hertz. So, a PIC 16F819 can be chosen, although any PIC with A to D capability would meet this criteria. Only the salient difference between PIC with analog input is their resolution. Some are say 8 or 12 bit, but most are actually 10 bit, okay, such as 16F819, that is PIC 16F819. Now, with a 20 megahertz oscillator, the PIC can sample 10 bits value at about 50 kilohertz. However, the limiting factor in the process is not the sampling rate, but the time required to transmit the digitized value to a PIC to a PC. Now, the fastest standard serial baud rate for the PIC is 38,400 bits per second, because each byte of data is limited to 8 bit. So, each 10 bit value is split up into actually the 2 bytes basically, okay, plus the start and stop bit for the each byte that has to be sent. Okay. So, for each 10 bit value requires 12 bit of data to be sent, 2 for the start bit, okay, for the 2 bytes, 2 for the stop, okay, for the 2 bytes. Consequently, the PIC can only send a digitized value at say 38,400 divided by 20, okay. So, at around 1920 hertz. Now, sending data in a constant stream like this, however, can easily cause the data to be corrupted on the receiving side. Now, if the clock of the transmitter and receiver are slightly out of synchronization, then the receiver, that is the PC, may lose track of where the bytes of data starts and where it is stops. Okay. So, to obviate this problem, a small delay can be introduced in the PIC basic before sending each value. Okay. So, for every 100 millisecond, the PIC estimates the muscle force based on the previous 100 millisecond of data. So, this much delay we can introduce on that. Okay. And also the estimated force is bind. Bind means that we give the designation basically. Okay. That is for an estimated force between say 0 and 5 pounds would be assigned to a bin 0. Okay. And an estimated force between say 5 and 10 pounds could be assigned say bin 1 and so on. Okay. So, the bin number directly corresponds to the position of the robotic arm basically. Okay. Corresponding to each bin there is going to be the position of the robotic arm, and this bin numbering is based on what amount of force is being extracted from your SEMG signal. Okay. So, every 100 millisecond the PC will send 2 bytes back out the serial port, the estimated force and the bin number. Now, the PIC 16F876 can be chosen as the microcontroller to interface the PC and the robotic arm, as I told you before, and the display the information on a LCD. Then next let us look at what are the necessary interfacing circuits basically. Okay. So, interfacing circuit the unit will comprise of says the signal conditioning unit, and this signal conditioning circuit must amplify the signal and filter out noise prior to digitization. Okay. And an instrumentation amplifier can be used for this purpose for primary amplification component as well as for the noise reduction component. Now, the voltage difference that will measure is the difference between the two electrodes placed on the biceps. Okay. And as the muscle action potential travels down the bicep, okay, the first electrode will become positive relative to the more distal electrode, and conversely as the action potential continues down the bicep, the second electrode will then become more positive, which of course means that the first will be becoming negative. So, that is how it is going to be. Now, in theory say ambient noise will reach the electrodes simultaneously, okay, and will not be amplified because the voltage difference between the two electrodes due to noise will be 0. To further eliminate the noise, high pass and low pass filters are implemented. Okay. So, a high pass filter of say 10 hertz is desired to reduce motion artifacts and the DC offset voltage, and a low pass filter of about say 500 hertz is desired to reduce high frequency noise. Okay. So, a low pass filter is important prior to analog to digital conversion to prevent aliasing. Okay. That is there, and a 0 to 5 volt input range is used on the analog to digital converter. Now, to ensure that SEMG amplitude is in the range, two more components are incorporated in the signal conditioning circuit. These are the full wave rectifier and an adjustable gain. Now, what does this full wave rectifier does? Full wave rectifier approximates the absolute value of the signal, because SEMG signal is bipolar. Okay, it can be both positive and negative. Passing it through a full wave rectifier will guarantee that the signal is entirely positive. Okay. And finally, an adjustable gain is useful to account for difference in electrode size, geometry and positioning, as well as differences among individuals, okay, all of which affect the amplitude of the signal. Now, the protocol that dictates how most serial communication is executed is RS-232. The protocol states, for example, say that a logic 1 is between say minus 3 volt to minus 25 volt, whereas say logic 0 is between plus 3 volt and plus 25 volt. Okay. As a PIC cannot output negative voltage, and because some PC serial ports have trouble reading voltages say less than 5 volt, it is good idea to use RS-232 level converter chips such as say Maxim Max 232. I am not discussing some of the details over here because of the time constant, and as I told you in the beginning, you can refer Professor Histand and Alcia Tor book for better clarification. These chips convert TTL CMOS level signal to say RS-232 level signal and vice versa, and it is important to note that they also invert the signal. Okay. So, for example, say given a plus 5 volt input, it will output about say minus 8 volt, and when given 0 volt, it will output about say plus 8 volt. These chips are able to provide these output using a 5 volt power supply and ground. This is made possible using a technique called charge pumping, which uses capacitors to store and boost voltage. Although the DB9 port has 9 pins here, only 3 are useful for our purpose. The other pins are for handshaking, a method to help regulate the data flow, which I have discussed in my earlier lectures. Now, next we focus our attention on the deciding on a programming language. Okay. So, since we are using the PIC microcontroller, PIC basic Pro is used as the programming language, and speed and memory constants are not primary concerns here. So, assembly language is not required. Okay. Also, the serial communication and the LCD interface commands provided by PIC Basic Pro will be quite useful, as I said in the beginning. So, next is draw the schematic. So, what we show the schematic figure for the conditioning circuit. So, we have instruction amplifier 939 gain, then you have high pass filter, and then there is a silent key low, and then we have the inverting amplifier, and then the precision full wave rectifier. So, next step is the draw the schematic. So, here what we can see that the signal first goes to the instrumentation amplifier, and then it goes through the high pass filter, and then there is a low silent key low pass filter, and then it goes to the inverting amplifier, and finally the precision full wave rectifier. So, this is the conditioning diagram. The first stage in an instrumentation amplifier with a gain of say 939, and the next stage is a simple RC filter followed by a buffer op-amp, and if the buffer op-amp were not included, then the resistance of the following stage would load the filter and change its behavior. Okay. So, it would not act as a simple RC filter. So, next is a 2-pole Sallen-Key low pass filter, a type of active filter. Okay. It exploits the feedback of an operational amplifier. Now, active filters are more robust than passive filters such as an RC filter, and that additional poles are better at attenuating unwanted frequencies. The next stage is the inverting op-amp, where the feedback resistor is a potentiometer used to adjust the overall gain of the system, and finally, in the last stage there is a precision full wave rectifier which requires no forward bias to turn on the diodes. So, next step is the draw a program flow chart. Okay. Here basically we declare variable and constants, and then define the AD con register that define how analog to digital conversion is performed. Then begin with the first analog to digital conversion, then there is a loop, wait for conversion to finish, store the analog to digital results in a variable, begin next A to D conversion, and send the saved A to D result out the serial pin and pass to get a delay between the bytes of data as I discussed in before, okay, and then it goes to the loop. And after initializing variables and defining how the analog to digital conversion is performed, the remaining portion is a simple loop that continuously samples the analog to digital converter and sends the data out through the serial pins. Now, interface PIC flow chart, if we look at, declare variables and constants as is done usually, disable analog pins, make them digital input output pins, define which pin will be used to interface that the PIC is working, flash the status LED to indicate that the PIC is working, and then we have a loop, get the two variable estimate force and bin number from the serial pin and display those value on the LCD and output the bin number on port A, in fact making it a parallel port, and then this can keep on going. So, this is the interface PIC flow chart. Now, PIC waits to receive 2 bytes on the serial port, estimated force and a bin number, okay. Display those values on the LCD and output the bin number on port A. Other than displaying information on the LCD, this PIC is essentially a serial to parallel converter basically, and the parallel value is what is read by the adept robot. Then coming to the next step, that is the writing of the code. So, PIC are 8-bit processor and any integer value over 8 bit must be stored in 2 or more registers. Okay. As the PIC 16F819 performs 10-bit analog to digital conversion, the result is stored in the 2 registers, addressal and addresses. One can choose how to justify the results, either the 8 least significant bits are in one register or the 8 most significant bits are on one register. The other 2 bits are padded with zeros. Justification conversion, which pin is being used for the conversion, initiating a conversion and other analog to digital parameters are defined by ADCON and ADCON1 register. Okay. You can see further in the data sheet of PIC 16F819. Then the last and the final stage of this mechatronics design is build and testing of the system. Okay. So, break the system down into smallest functional units and test the input and output of those units to ensure they are performing as expected. The signal conditioning circuit, for example, we could test just like just the full wave rectifier by passing a sine wave through it and confirming that the output signal is getting rectified. Also, each of the filter could be tested by inputting a frequency sweep and confirming that the amplitude at the cutoff frequency is about 70.7% of the input amplitude. And with any peak, it is good idea to include a status LED that indicates that the peak is on and functioning to some degree. While troubleshooting, it is also useful to flash the status LED at different points in the code to help you track the execution. And LCDs are as I said before, extremely useful once they are functioning in debugging codes, because they can easily be used to display diagnostic messages and values before being stored in the variables. Serial communication between PIC and PC can be tested using the terminal program. Hyperterminal, the terminal program bundled with Windows, allows you to read from and write to the serial ports. One just needs to be sure to specify the port setting actually, that is such as the baud rate. Okay, so that they match the format that the PIC is sending or expecting to receive. So, this is the reference which I talked to you, that is Introduction to Mechatronics by L.C. Atoor and Histon by Tata McGraw-Hill 2012. There are many other editions of it also available. So, you can refer this textbook for further details. Thank you.